So 8.1 is the start of our work with vectors, and we're going to be working with vectors for a few days here and then eventually going into polars. Vectors, you might have a little experience with vectors, well, a lot of experience in physics. If you took our trig course, you have a little more experience also. Otherwise, I think for some of our Honors Algebra 2 kids, this might be the first time. So the difference between, well, there's a lot of differences. But when you have a vector, you have both magnitude and direction. So we think of rays as like what they look like, but they're not really rays, right? Magnitude could be a measurement of, they call it size sometimes, but it could be a measurement of speed or distance. But that's not the only component to a vector. You also have the direction or the angle, which sometimes we refer to as bearings. Yes, the dreaded bearings are back. So when we kick a football, the angle that it makes with the ground when it's kicked, plus the velocity at which it's kicked. So that sounds really familiar. Didn't we just do parametrics where we had the angle at the ground and then the initial velocity and the initial height, and we had our parametric equations? Well, our lesson today is we're going to start describing things in terms of vector components. So I don't know if it's assigned to you still, but on some of your homework, I kind of shortened it a little bit. They ask you whether it's a vector or just what's called a scalar quantity. So a vector would have both size and direction, and a scalar quantity would just have size or magnitude of some sort. It would have no direction. So when I look at part A, a boat traveling at 15 miles per hour, that is a speed, so that would be the magnitude component of it, but there's no direction. So that means that we have a scalar quantity. And then our hiker is walking 25 paces due west. So the 25 paces is the distance or the magnitude of the vector, and due west is the direction. So because we have both magnitude and direction, we have a vector. And then this one always messes with my brain. I'm sure it messes with yours the more you think about it. The person's weight on a bathroom scale. So when the scale measures a person's weight, it is calculating the acceleration due to gravity, how far you're being pulled down because of the gravity. So like your weight on Earth would be a different weight on the moon because of the gravity force. So because of that, it's actually a vector. So that was that's quite a trick question actually, because it's measuring, pulling down and then the force of gravity with it. So that's kind of weird. This again is on the homework, but it's not on your notes. So if you're looking at your notes, you're not going to find this part. A car traveling 60 miles per hour, 15 east of south. So this is our direction. This is our magnitude. So we have a vector. All right, so stuff like that. I'm going to move on. That's kind of boring. All right, so what does a vector look like? When we graph a vector, it looks a lot like a ray, but sometimes they'll put a dot at the end, or sometimes you'll see a little line like this indicating that it literally ends. So arrows do not indicate that it goes on forever. So this, the length of what looks like a ray, it's actually a vector, is supposed to be drawn proportional to some mystical scale that you create. Now when we draw vectors in our class, I'm not going to make you make a scale. So like literally you'd have to get out a ruler, kind of, or at least estimate and say like, okay, every 1 centimeter represents 10 feet, and then measure out how far out the vector literally would have to be according to that scale. We're not doing any of that stuff. But some more vocabulary for you for a vector. Our initial point to the terminal point, this is called the tail, and then the end is the tip. So that is the direction in which it travels, and then the actual bearing that's associated with that is going to be most likely the direction that we're going to be referring to. Because often they're not going true north, true south, true east, or true west. They're usually off of one of those quadrantals. So in standard position, the vector is very easy for us to locate the direction because it's a lot like our trig work. So off of the positive x-axis, the direction is just like how we used to do with trig. So like that should seem very, very common, right? And this is talking about that scale business. They have a scale down here. 1 centimeter is 5 feet. So if this vector is supposed to be 13 feet long, we are going to label it as 13 feet. But technically when we draw it, we're supposed to do the proportion and figure out, I don't know what I was going to figure out. I forgot what the problem was already. So you had to actually measure the vector and have it that long, like with a ruler, or at least estimate it that long. guys, I can't draw, so I can't measure either. I really can't do anything as far as like artistic skills, so I'm not going to bother with that part. As long as you label your vector with the appropriate magnitude, we'll call it a day. So now, finally, we're on our notes. So remember our vocab. A scalar is a quantity that has magnitude only, no direction. A vector has both magnitude and direction. So one of your tasks is to figure out whether we're looking at a scalar or a vector. And the direction of the vector is the angle between the vector itself and the positive x-axis. But we're going to find out next that that's not the only way they can measure things, of course. So you can have a bearing. And a bearing can go off of the north-south line, either one. And the notation in which they use tells you how to read the bearing. So we'll talk about true bearings in a minute. True bearings, I believe, are what your trig book did here at our school at Harlem. And I think true bearings are used a lot in air traffic control, because when you're doing calculations, like you don't want to have to consider like, oh wait, am I going off the north line or the south line? Like they always have one point of orientation, or one line of orientation. Anywho, let's get back to quadrant bearing. So they use the phi symbol, which when you hand draw it, it looks an awful lot like a P, huh? It's a Greek phi. And the directional measurement between 0 and 90, east or west of the north-south line. So what you're going to notice is it's going to have one of the north or south lines first, and then a direction, angle, and then a direction at which to travel. So whatever this first one is, this is the line that you start at, and then you go towards this other one. So the example they have here is south 35 east. So you start at the south line, and then you travel towards the east line 35 degrees. So it turns out that vector has a direction of that, but we could also label it 145 degrees of a true bearing, because true bearings always go off of the north line. So if you have to start off the north line and then travel kind of weird, you gotta go clockwise just to really mess with you, right? This is 145 degrees from here to the vector. So this bearing and the bearing of 145 degrees is the same thing. If I notice that you have a true bearing, they're going to always label them with 3 numbers. So 25 degrees is going to be measured as 025 degrees. That's the indication that you are looking at a true bearing. Otherwise, it'll just flat out say you have a true bearing. Now, a lot of ours are going to be off the horizontal line. So I think that's one of the most difficult parts, is figuring out like where exactly is this direction of the vector trying to describe. And if they don't give you a picture, it's extra exciting. All right, so this is not in your notes, but this is a good diagram to look at. So pretend we did the scale thing and we drew it beautifully, I'm sure. So we have 20 feet per second, which I'm going to label right here. And then it says that a bearing of 030, which means off of true north. So they traveled clockwise 30 degrees. There you go. That's what it looks like. Now the vector itself, and this is a little confusing, is this, with this label. And the angle being labeled is important as well. So it's not, like all parts of that are not the vector. It's the thing that looks like a ray, but we now know it's a vector. If it bothers you that they look like rays, what I usually do is I put a little mark at the end of it like that, so like my brain goes, okay, that's a vector, not a ray. The nature of the problem is pretty obvious, that it's a vector also. So here we have 30 miles per hour, so there's your magnitude, which we need to label here. And then the bearing this time is south 60 west. So you start at the south line, and then you head towards the west 60 degrees. There we go. Alright, so now we're back to your notes. They want us to draw this, so I always start with the bearing itself, and I'll come back and label the magnitude, 125 degrees to the horizontal. So when they say that, they're referring to the positive x-axis. So 125 degrees, drawing it like I used to do in trig, 90, 125 would be like right here. And I can put a little end here if that makes you happy. So this, from here to here, is 125 degrees. And the magnitude of that vector is 60 pounds. That says pounds, you just can't read it. Alright, we're going to come back to this question in a little bit once we learn about the components. So here we have 55 miles per hour at a bearing of south 45 east. So if we start at the south line and we head towards the east line 45 degrees, I end up right there. which technically I traveled this direction, but turns out both of these angles are 45 degrees. And then the magnitude here is 55 miles per hour. And again, if it makes you happy to put a little cap on the end of that so you know it's a vector, go right ahead. Alright. A little more. So this time we're going to start at the north line and head towards the west. So 40 degrees westward, like here, vector, and we traveled like this, 40 degrees, and the magnitude was 30 meters. And then for part 4, we have 20 degrees to the horizontal. So like right there, the vector ends. This right here is 20 degrees. Sometimes I draw exaggerated angles that aren't really to scale simply because my handwriting's so bad I need a larger angle. So, larger picture at least. 150 yards is the magnitude on that vector. Beautiful drawings as always, Mrs. Abuso. Very good, very good. So parallel, equivalent, and opposite vectors. These are vocabulary terms that we're going to need a lot when we do especially the parallel vectors. We're going to need to notice where parallel vectors are in our pictures when we go to do bearing applications. That's tricky stuff. But we have to be able to identify who's parallel. So when I look at the definition of parallel, they have the same or the opposite direction, but not necessarily the same magnitude. So I think everybody here is parallel except for D. Like everybody else is parallel to each other. So that's what's going on there. Yep, that's what they said here. A, B, C, E, and F are all parallel. But if you have equivalent vectors, this time they have the same magnitude and direction. And they're saying A and C, boom and boom. So they are literally the same size or magnitude, and they are going in the same direction. Some kids will argue, well, what about E? Well, E is going in the opposite direction of those two, so that's not going to work out. And the other ones are either the wrong size or the wrong direction. So only A and C are equivalent vectors. And then opposite vectors, this one is always, I don't know why it's hard for me to see, but it is. They have the same magnitude, so same size, but they're going in opposite directions. So I think A and C are opposites. And since A and E are opposite, there we go, A and E. But remember how A and C are parallel? So also C and E are opposite vectors. I feel like I missed some sort of a combo here. I don't know. So they're the same size going in opposite directions. That's the thought. Alright, now we're going to talk about how to convert these to rectangular components, which we know is our X and Y, or horizontal and vertical components. So very much a trig problem, right? And technically a geo problem. We're going to be using our right triangle trig. If you've had physics, you see a lot of physics. Alright, so finding the horizontal component, X, we're going to use our trig, and same thing for Y. Let's talk about how we're going to do that. So, this question, let's skip ahead. Let's go to this question. So we have our lawnmower, and they're talking about the force being pushed down, and they tell me a 56-degree angle with the ground. So if I think about, okay, how would I be solving for X? Well, this is a right triangle problem involving adjacent and hypotenuse, so that's a cosine problem. So we have the cosine of 56 degrees equals X over 450. So if I thought about how I'm going to solve for X, I would multiply 450 times the cosine of 56. And then same thing for setting up a proportion for Y. I'd say the sine of 56 equals Y over 450. And then if I'm trying to solve for Y, I'd multiply 450 times the sine. So we're going to notice that there is a definite pattern here when it comes to finding horizontal and vertical components. If you have the angle that your vector is making with the positive horizontal axis, which would be the ground in this case, but the positive horizontal axis, if you can figure out that angle, you can always use the formula, which I think is on a page coming up here, right here. The horizontal component, which is X, is always going to be your magnitude, or your R they call it, times the cosine of the angle that you make with the ground is the way you can think of it, or the positive, the angle with the positive x-axis. And the vertical component, or the y, can always be found by taking the magnitude, or the r, and multiplying it by the sine of the angle with the positive x-axis. So again, it has to be the angle with the positive x-axis. If you were working with a bearings question and it's not with the positive horizontal axis or the ground, you have to do a little bit of work and figure out what that angle is if you want to use this formula. And I think this is how they do this in your physics class, at least in the, I know one of the physics, the regular physics maybe? I'm not sure. We're going to do some really crazy bearings questions coming up where we have to use some law of sines and cosines. All right, we have Jamal, and he is pulls on an end of a rope that's tied to a dinghy, and he's using a force of 50 newtons. So they already labeled our picture for us. They have the angle that it's with the horizontal is 60, and they want you to find the horizontal and vertical components. So for Jamal, the magnitude is this guy here. So he's going to take 50 newtons and multiply it by the cosine of the angle they make with the ground, or the horizontal, 60 degrees. And then for the vertical component, it's the magnitude again, so 50 times the sine of 60. So, I think I already did this one. I'm going to kind of steal the answer. Actually, I think it's done on your paper, but that's all right. So this comes out to about 25. I don't know if it's exact newtons. And this one comes out to 43.3 newtons. Oops, 3 newtons. There we go. So that's a nice little trick. And again, only works if you have the angle with the positive x-axis. You got to do a little work if you don't have the angle with the positive x-axis. So here, instead of magnitude, they used r. So just write yourself a little note that r represents the magnitude. If you want to kind of relate it to your work with trig, it's like the radius of our triangles that we were using on the unit circle stuff. So now that I want us to go back to numbers 1 through 4 and find all the horizontal and vertical components, I'll do that for a couple of them. I'm not going to do all 4. I'm just too lazy right now. Let's do this one. All right. So the horizontal and the vertical component. So it's the magnitude, which is 60 pounds, times, and then even though it's an obtuse angle, that's still the angle we want to use. It's the angle with the positive x-axis, so that's 125 degrees. So cosine of 125, and this one's going to be 60 times the sine of 125. Now remember how coordinates work. If this is your vector, your x-coordinate should be negative, right? And your y-coordinate should be positive, so don't be surprised when that happens on your calculator, right? So, I think somebody already calculated. I'm going to steal some answers from my favorite partner teacher there next door. She already did this problem. So, let's see. This one comes out to negative 34.4. What's the description here? Pounds of force. And then this one comes out to 49.1 pounds of force. Should use an L there. Looks like a 1. That's confusing. All right, there we go. I do want to look at one of the negative ones, though. Yeah, let's... no, they're all good. Let's look at number 2, and then we'll call it a day for that. So, horizontal and vertical components here. So our magnitude is 55 miles per hour. And then remember, it's the angle it makes from the positive x-axis. So getting down to this vector, we'd be traveling negative 45 degrees, right? So you'll have to think about direction here, because you want to make sure that your components come out with the appropriate sign. So the x-coordinate is going to be a positive answer here, but when I type in this vertical or y-coordinate, you should get a negative one. So hopefully that works out well. Let's find out. Let's steal my answers from my friend. 38.9 for the horizontal, and this was, what's the label here, miles per hour. And then also, oh duh, because it's a 45 degree angle, Abruzzo, hello, 38.9 miles per hour on the vertical component. Notice it's negative though because of the direction. If we put positive 45, we would have got 2 positive components, which was not accurate. All right, back to our notes. Where did we leave off? So we pretended we did 1 through 4. We only did 1 through 2. Sorry. All right. Remember those quadrant and true bearings? It's about to get real, guys. All right. So I think that's the most difficult part on setting them up, is making sure that you have things in the right spot. Now, I'm going to tell you that often we have a picture that is true to form, like it's to scale and everything, but when I go to do my math, like law of sines and cosines, what we're going to learn later, the picture is really hard to read. So sometimes I redraw the triangle that is formed off to the side, and I exaggerate the angles a little bit so they're not going to be true to form anymore. I need space to write numbers, frankly. You do want to make it to scale as possible the first time around so you can see the relationships, and then once you have those in, you can fill in the numbers separately. All right. Anyways, I'm digressing a little bit and jumping ahead. So here, all they want me to do is draw it and then find the horizontal and vertical components. We got this. So 120 degrees from the horizontal means just like a trig problem, right? So from the horizontal, 120 degrees measures this away. I feel like we did this question, maybe not, I don't know. So it's 7 inches is the magnitude, label and everything. This is 120 degrees. It's kind of a boring question now, guys, because we just did a couple of these and they're the same. So the horizontal, which is the x, and the vertical, which is the y, can be found by taking the magnitude and multiplying it by the cosine of 120, that's the correct angle, and then 7 times the sine of 120. So if I think about how this is going to work out, we want to make sure that the x comes out negative and the y comes out positive. So when I type this in my calculator, again, I'm going to kind of steal an answer from my buddy. She's all right with it, I promise. All right, let's see. What do we change here? There we go. So I'm going to write them in, it looks like an ordered pair, but because it's a vector, they use these weird little arrows. So this is negative 3.5, comma 6.1. Lovely. All right. So same thing here. I need to draw it first, especially this being a weird bearings question. So you start at the north, which is right here, and you go towards the west 50 degrees. So like here. So this right here is 50 degrees. But when I think about the actual angle that I'm going to use in my calculation, this is 140 degrees, isn't it? So the magnitude is 2.5 centimeters. Sorry for the loud bell if you can hear that. And my vector components are going to be 2.5 times the cosine of the entire angle of 140. And, oh, you know what? Scratch this. Apparently this question has changed. So that would have been the right way to do that question, but if I look on your paper, this has been changed to east. So that is a big difference, guys. Look at this. Still starting at north, but now we're going 50 degrees east. So like here. Okay. Now, if I think about what angle they want this angle, which is a 40-degree angle. The magnitude is still 2.5. Okay, well that is a horse of a different color. All right, here we go. The horizontal component is going to be 2.5 times the cosine of 40. There we go. And 2.5 times the sine of 40 is my vertical component. So I think that's what's on your paper, the one that we printed for you. So let's go with that example. All right, so these come out to, looks like 1.9 and 1.6 respectively. Let me pause for a minute. All right, so I'm just going to do number 7. Number 8's like super duper easy, so I'm just going to skip it if you don't mind. Because it's like half answered for you. Number 7 says a true bearing. So this is that weird one that like your trig book always goes off of north of, and then it goes clockwise just to really mess with you. 140 degrees true north would be like doo-doo-doo down here. So if this is 140 degrees, then I need to figure out the angle it makes with the positive x-axis. So just from here to here. So 90 minus, well, 90 from 140 is 50 degrees, but it's negative 50 degrees, isn't it? It's going down from the positive x-axis. So my horizontal component would be, and a bearing of, or magnitude of 4. So 4 times the cosine of negative 50, so I get the right signs, and then 4 times the sine of negative 50, so I get the right signs. Boop. And when I type that in, I'm sure those sound effects really help, right? 2.6 comma negative 3.1 are my horizontal and vertical components. All right, so skipping 8, it's boring, and now it's about to get